Hello, my name is Sharareh Shirzad and I'm a graduate student at Louisiana State University. And this video is part 2 from the project related to enhancing the durability and service life of asphalt pavements through the application of an innovative light-activated self-healing polymer. In this section, I will provide some information related to the application of self-healing polymer in asphalt binder and also asphalt mixture. In order to prepare the polymer modified asphalt binder, first we need to decrease the particle size of the polymer. A grinding machine with a 24,000 RPM was used to decrease the size of the polymer. Next, the asphalt binder was heated in an oven with the temperature of 163 degrees C, and then a specific amount of binder is poured in a metal can. The metal can containing the asphalt binder was placed on a hot plate to maintain the temperature of 163 degrees C. A high shear stirring machine was used to provide a RPM of 3600, and then polymer was added to the binder slowly. After adding all the polymer to the asphalt binder, mixing is continued for 36 minutes at 3600 RPM and 163 degrees C. After preparing the binder blends with or without self-healing polymer recycled materials, different chemical tests can be used to study aging and molecular characteristics of binder. FDIR was used to evaluate oxidative aging of prepared binder blends with or without self-healing polymer through the formation of specific functional groups. Aging of asphalt binder causes an increase in the carbonyl and sulfoxide absorbance, respectively around 1600 and 1030 peaks. Carbonyl and sulfoxide index can be defined as the ratio of area around these peaks divided by a reference area. The aliphatic group is usually selected as a reference group since they are considered stable during the aging process. The increase in the ratio is an indication of higher levels of oxidation and therefore a stiffer binder. GPC provides the molecular weight distribution of asphalt binders component. The molten or low molecular weight components with an average molecular weight less than 3,000 daltons, while molecular weight of asphaltenes is between 3,000 to 15,000 daltons. Using this approach, the aging and brittleness levels of asphalt binder can be evaluated through the change in the ratio of asphaltenes and maltenes molecular weight. Different tests were performed on the prepared binder blends with or without self-healing polymer and recycled materials to evaluate rheological properties of the prepared binder blends. Rotational viscometer was conducted to measure the viscosity of the binder blends, while dynamic shear rheometer was used to measure the complex shear modulus and phase angle of different binder blend samples. For the low temperature performance of the binder blends, bending beam rheometer was used to measure stiffness and relaxation at low temperature. Finally, multiple stress creep recovery test was conducted to evaluate elastic recovery of different. In order to evaluate the effect of self-healing polymer on the self-healing performance of asphalt mixtures, slabs are compacted using the polymer modified binder. Next, rectangular beams were cut from the slab. Using a 3-point bending setup, cracks are induced on the bottom of the beams. After creating the crack, samples are placed under two different curing conditions, room temperature and high temperature. For samples containing UV light activated self-healing polymer, the high temperature curing condition was replaced with UV light exposure. Healing efficiency of samples was measured using two different approaches. In the first approach, a light microscopy was used to take pictures from the cracks every day for 6 days. An average crack width was calculated for each crack, and healing efficiency was measured as the difference of crack width after healing and initial crack width divided by the initial crack width. In the second approach, the strain energy of samples, which is defined as the area under the load displacement curve up to the peak load, is measured in two states. One, when crack was induced or initial strain energy, and two, after 6 days of healing or healed strain energy. Strain energy recovery ratio is calculated as the healed strain energy divided by the initial strain energy. Finally, laboratory tests were conducted to study the performance of asphalt mixtures containing the optimum percentage of self-healing polymer against cracking at intermediate and low temperature and rotting. Semicircular bending test measures the critical strain energy release rate to examine the cracking performance of prepared mixtures at an intermediate temperature. The resistance to permanent deformation of mixtures was evaluated using the LWT, where cylindrical specimens were submerged at 50 degrees C, and a steel wheel was passed across the surface until attainment of 20,000 cycles at a rate of 56 passes per minute. The thermal stress-restrained specimen test was used to determine the tensile strength and temperature at fracture. The prepared beams were attached to the machine and placed in an environmental chamber for conditioning. A tensile load of 50 Newton was applied to the sample while cooling the sampling at a rate of 10 degrees per hour. Cooling was continued until fracture failure of the samples was observed. Thank you for watching this video. For more information about this project, please visit Tran-SET.lsu.edu.